Our next and last step for today will be to take control of allocation. That is, currently our interpreter uses +k to construct a record that has 3 fields, say. So there's the 3 fields inside the record, and there's also its identity as +k that we're constructing here. We're going to take control of that by writing our own memory allocator, and the malloc3 here, the 3 is because we need space for 3 fields. In addition to those 3 fields, we use a tag here, 1, which means +k as opposed to done_k or mult_k or something like that. The result of malloc is not going to be a record, it's just going to be a number representing an address in memory. Everything that we deal with in our interpreter now will just be a number. Some of those numbers represent tags, like 1, and some of them represent values, like the value inside of an int v, and some of them represent addresses. In the case of a +k, all 3 things here turn out to be addresses. Where I used to write r, meaning an r that was pattern matched out of the enclosing +d, now I have that +d in the expression register, but that's just an address in memory. And to get the r part of that piece of code, I need to take the memory and look at offset 2 to get the address of the sub-expression. So ref here is going to go along with malloc, whereas malloc allocates memory, ref will look into memory and tell me what's there. I need to pick a tag for each of our different variants, and I'm going to pick unique tags for all the variants. So 0 will mean done_k, 1 will mean +k, and so on. I don't have to allocate any new code at interp time, but I do have to look at different kinds of code records like int_d and +d. So we will need tags for those as well. And finally, we do need to allocate new values, new ints and closures at runtime, and so we have tags for those. These tags replace the use of a pattern matching match in our interpreter and continue functions, where we used to match on this register that had a record in it, and then pattern matching would pull out the pieces for us. Now our registers just have addresses into memory, and we have to look inside of memory at offset 1 from that address to get the tag, like 0, 1, 2, or 3, and then we use match just to match on a number. So this Shplait code using the match form that's just on numbers could easily be converted to assembly code that compares numbers and branches. Once we match on a particular number, like 3 means mult_k here, then 3 does not mean mult. Then we can pull out the pieces of what used to be a record by looking into memory at the various offsets. So offset 1 here corresponds to the r field, offset 2 corresponds to the environment field, offset 3 corresponds to the k field. We implement our malloc and ref functions by having our own representation of memory. So memory here is going to be an array of 1500 numbers, where all the numbers are initially set to 0. And to allocate memory, we need a register that represents our allocation pointer. So we're going to initialize our allocation pointer to memory address 0. What a function like malloc does then, malloc3 say, which takes a tag and then 3 values for the content of that record, it is going to take our current allocation pointer and at offset 0, put the tag there, and at offsets 1, 2, and 3, put the values a, b, and c. Finally, we need to increment the allocation pointer by 4 because we need space for the tag plus the payload options. And finally, we return the old value of the pointer. So this incrementing the pointer and then subtracting 4 back off just avoids having to use a local variable, which is not very assembly-like. So this makes all allocation explicit, and notice that everything is a number. So memory is an array of numbers, malloc returns a number that you can use as an address into memory.